Close your eyes for a moment and imagine the vast expanse of space stretching out before you. In the cosmic ocean that surrounds our planet, among the countless stars that twinkle in the night sky, there exist objects so mysterious, so profound, that they have captivated humanity's imagination for generations. These are the black holes regions of space-time, where gravity pulls so strongly that nothing, not even light itself, can escape their grasp. Tonight, we embark on a peaceful journey through the darkness, exploring the nearest black holes to our home planet Earth. These cosmic entities, once thought to exist only in the realm of theoretical physics, are now known to be real, tangible objects scattered throughout our galaxy. Some are closer than you might imagine cosmic neighbors in the grand scheme of the universe. As we drift through this narrative, let your mind wander among the stars. Feel the gentle pull of curiosity drawing you deeper into the mysteries of space. There's something profoundly calming about contemplating the vastness of the cosmos, about understanding our small place in this infinite theater of existence. The black holes we'll discover tonight are not the monsters of science fiction. They are natural phenomena, the inevitable endpoints of stellar evolution, peaceful in their eternal dance through space. Each one tells a story of birth, death, and transformation. Each one holds secrets that scientists are only beginning to unravel. So settle in, take a deep breath, and prepare to explore the invisible giants that lurk in our galactic backyard. Let the gentle rhythm of cosmic discovery lull you into a state of peaceful contemplation. Chapter 1. Understanding the Invisible. Before we meet our nearest cosmic neighbors, let us first understand what black holes truly are. Imagine a star much larger than our Sun, perhaps 10, 20, or even 50 times more massive. For millions of years, this star burns brightly, fusing hydrogen into helium in its core, generating tremendous pressure that pushes outward against the relentless pull of gravity. This delicate balance pressure pushing out, gravity pulling in sustains the star throughout its life. But all stars must eventually exhaust their nuclear fuel. When a massive star reaches the end of its life, when the last of its fuel has been consumed, there is nothing left to counteract gravity's inexorable pull. In a moment that lasts mere seconds, but releases more energy than the star produced in its entire lifetime, the core collapses. The outer layers explode in a spectacular supernova, briefly outshining an entire galaxy. But the core continues to fall inward, collapsing beyond any known physical state, crushing matter into an infinitely dense point called a singularity. Around this singularity forms what we call the event horizon, an invisible boundary that marks the point of no return. Anything that crosses this threshold, whether matter, energy, or light itself, can never escape. The black hole doesn't suck things in like a cosmic vacuum cleaner, as popular culture might suggest. Rather, it warps space-time so severely that all possible paths forward lead only inward. This warping of space-time is one of the most elegant predictions of Einstein's general theory of relativity. Space and time themselves become curved in the presence of mass and energy. Near a black hole, this curvature becomes so extreme that our normal understanding of physics breaks down. Black holes come in different sizes. The ones formed from collapsed stars, called stellar mass black holes, typically range from about 3 to several dozen times the mass of our Sun. These are the black holes we find scattered throughout our galaxy, the ones that exist in our stellar neighborhood. They are distinct from the supermassive black holes that lurk at the centers of galaxies, which can be millions or billions of times more massive than our Sun. The beauty of black holes lies not just in their mysterious nature, but in their simplicity. Once formed, a black hole can be completely described by just 3 properties: its mass, its spin, and its electric charge. Everything else about the star that formed it, its chemical composition, its magnetic field, its complex structure, all of that information is lost forever. This is what physicists call the no-hair theorem, a somewhat whimsical name for a profound principle. Detecting black holes presents unique challenges. By definition, they emit no light. We can only observe them through their effects on nearby matter and space. When gas and dust fall toward a black hole, friction heats the material to millions of degrees, causing it to emit X-rays before crossing the event horizon. When a black hole has a companion star, we can observe the star's orbital motion, allowing us to infer the presence and mass of the invisible partner. As you contemplate these cosmic enigmas, remember that they are not aberrations or anomalies. They are natural consequences of the laws of physics that govern our universe. In a very real sense, black holes are as natural as stars, planets, or galaxies themselves. Now that we understand what black holes are, let us turn our attention to the specific black holes that exist nearest to Earth. These are not abstract theoretical constructs, they are real objects, occupying specific locations in our galaxy, each with its own unique characteristics and story. For many decades, astronomers suspected that stellar mass black holes must be relatively common in our galaxy. After all, massive stars exist in abundance, and the laws of physics dictate that when such stars die, many should form black holes. But finding these dark objects proved extraordinarily difficult. The breakthrough came through careful observation of binary star systems, pairs of stars orbiting their common center of mass. In some of these systems, astronomers noticed something peculiar. One of the stars appeared to be orbiting an invisible companion. By studying the visible star's motion, scientists could calculate the mass of the unseen partner. When that mass exceeded the theoretical maximum for a neutron star, about 3 times the mass of our Sun, they knew they must be observing a black hole. The landscape of our knowledge about nearby black holes has been revolutionized in recent years by the European Space Agency's Gaia mission. This space telescope has been precisely measuring the positions and motions of over 1 billion stars in our galaxy. By analyzing tiny wobbles in stars' motions, Gaia has revealed previously unknown black holes that were completely invisible to us. What emerges from this cosmic census is a picture of our galactic neighborhood populated by dozens, perhaps hundreds, of these dark sentinels. They orbit through space in silence, some alone, some accompanied by companion stars in their gravitational embrace. They range in distance from us from about 1,500 light-years to several thousand light-years, close enough to study in detail, yet far enough that we need never worry about their gravitational influence on our solar system. Each of these black holes has its own personality, if you will, its own mass, its own spin rate, its own history. Some were born recently, cosmically speaking, within the last few million years. Others have been drifting through space for hundreds of millions of years, silent witnesses to the evolution of our galaxy. As we explore each of these objects individually, imagine yourself as a cosmic explorer, charting these dark territories for the first time. Each black hole we discover tells us something new about the universe, about stellar evolution, about the extreme physics that governs matter under the most intense conditions imaginable. Let us now meet these cosmic neighbors, one by one, starting with the closest known black hole to Earth. At approximately 1,560 light-years from Earth, nestled in the constellation Ophiuchus, lies what is currently known as the closest black hole to our planet, Gaia BH1. This discovery, announced in late 2022, fundamentally changed our understanding of black holes in our cosmic neighborhood. For years, astronomers had suspected that closer black holes must exist, but finding them proved elusive. Gaia BH1 was discovered through its gravitational influence on a companion star, a sun-like star that orbits the black hole every 185 days. The Gaia Space Telescope detected the subtle wobble in this star's motion as it circles its dark companion. The black hole itself has a mass approximately 10 times that of our Sun, a fairly typical mass for a stellar mass black hole. What makes Gaia BH1 particularly interesting is its quiescent nature. Unlike many known black holes, which are actively consuming material from companion stars and glowing brightly in X-rays, Gaia BH1 is remarkably quiet. It's not currently feeding, making it much harder to detect, but also making it more representative of the typical black hole population in our galaxy. Picture this system in your mind: a star much like our own Sun, going about its business of fusing hydrogen into helium, shining steadily into space. But instead of having planets orbiting it, as our Sun does, this star shares its space with an invisible companion, a region of collapsed space-time 10 times more massive than itself. Every 6 months, the star completes one orbit around their common center of gravity, a cosmic dance that has been going on for millions of years. The companion star in this system gives us a unique window into the black hole's properties. By carefully studying the star's spectrum, the rainbow of colors in its light, astronomers can measure how fast it's moving toward or away from us at different points in its orbit. This Doppler shift, the same phenomenon that changes the pitch of a passing siren, allows us to precisely calculate the mass of the invisible partner. What's particularly intriguing about Gaia BH1 is what it tells us about black hole formation. This black hole likely formed from the collapse of a massive star sometime in the distant past, perhaps 100 million years ago, perhaps more recently. The star that collapsed was probably 15 to 20 times the mass of our Sun, a brilliant blue giant that burned through its nuclear fuel relatively quickly. When that progenitor star exhausted its fuel and collapsed, it likely did so relatively quietly, astronomically speaking. Not all supernova explosions are violent enough to completely disrupt a binary system. In this case, enough of the system remained intact that the companion star stayed bound to the newly formed black hole, continuing their orbital dance even after the dramatic transformation. The discovery of Gaia BH1 suggests something profound. There may be many more quiescent black holes lurking in our galactic neighborhood than we previously suspected. Most of our black hole discoveries have come from finding systems that are actively accreting matter glowing brightly in X-rays. But if Gaia BH1 is representative, there might be 10 or even 100 times more black holes that are simply too quiet to detect with traditional methods. Imagine the implications of this. Our galaxy might be filled with these invisible entities, dark objects drifting through space, occasionally betraying their presence through subtle gravitational effects on nearby stars. They pose no danger to us. Space is so vast that the probability of Earth ever encountering a stellar mass black hole is essentially zero. But their existence reminds us that the universe is far stranger and more mysterious than our everyday experience might suggest. As you contemplate Gaia BH1, 1500 light-years away, remember that the light by which we see its companion star left that system around the time Rome was founded, when classical civilization was just beginning to flourish on Earth. The black hole itself, of course, emits no light. It exists as a fundamental absence, a place where light goes to die. Shortly after the discovery of Gaia BH1, astronomers announced another nearby black hole discovered by the same Gaia spacecraft, Gaia BH2, located approximately 3,800 light-years from Earth in the constellation Centaurus. This discovery was particularly exciting because it confirmed that the techniques used to find Gaia BH1 could be applied to uncover more of these dark objects. Gaia BH2 is notably more massive than its closer cousin, weighing in at approximately 8 to 9 times the mass of our Sunday. Like Gaia BH1, it has a stellar companion in this case, a red giant star that has already left the main sequence of stellar evolution and expanded to many times its original size. The orbital period of Gaia BH2 and its companion is longer than that of Gaia BH1, about 1,277 days, or roughly 3.5 years. This longer period reflects the greater separation between the two objects. The red giant star is far enough from the black hole that it's not currently being stripped of its outer layers, allowing us to observe the system in a relatively pristine state. What makes Gaia BH2 particularly interesting to astronomers is its evolutionary implications. The red giant companion star is in a later stage of stellar evolution than the Sun-like star that orbits Gaia BH1. This tells us something about the history of the system and raises intriguing questions about its future. Stars evolve at rates determined by their mass. More massive stars burn through their fuel faster and die younger. The fact that the companion to Gaia BH2 has already evolved into a red giant, while the black hole exists as a stellar remnant, suggests a complex evolutionary history. The star that formed the black hole must have been significantly more massive than its companion, allowing it to evolve faster and die first, leaving behind the black hole we observe today. But the story doesn't end there. The red giant star itself is approaching the end of its life. In perhaps a few million years, an eye blink in cosmic time, this star too will exhaust its nuclear fuel. What happens next depends on its mass. If it's massive enough, it might also collapse to form a black hole, creating a binary black hole system. If it's less massive, it will likely end its days as a white dwarf, a dense stellar remnant that will slowly cool over billions of years. The discovery of Gaia BH2 at a distance of 3,800 light-years reinforces the idea that black holes are not rare cosmic oddities, but rather common outcomes of stellar evolution. If we can find two nearby black holes using the Gaia data, there must be many more waiting to be discovered as we continue to analyze the telescope's observations. Consider what 3,800 light-years means in cosmic terms. The light we see from the red giant companion left that system when humans were just beginning to develop agriculture and settle in permanent communities. Civilizations have risen and fallen. Empires have come and gone, but throughout all of human history, this binary system has continued its slow cosmic waltz, the red giant star faithfully orbiting its dark companion. The region of space between us and Gaia BH2 contains perhaps 1 million stars, uncountable planets, nebulae where new stars are being born, and the diffuse gas and dust of the interstellar medium. Yet despite all this matter, space remains overwhelmingly empty. If you could somehow travel from Earth to Gaia BH2, you would spend most of your journey in darkness, punctuated by the occasional passage near a star. Gaia BH2 reminds us that the universe is full of objects we have yet to discover, phenomena we have yet to understand. Each new black hole we find adds another data point to our understanding of how these objects form, how they evolve, and how common they are throughout the galaxy. Moving outward in our exploration, we come to V616 Monoceratis, also catalogued as A62000, located approximately 3,300 light-years from Earth in the constellation Monoceros. This black hole has a special place in astronomical history as one of the first stellar mass black holes ever discovered, and it remains one of the best studied examples of its kind. Unlike the quiescent black holes Gaia BH1 and BH2, V616 Monocerotis is what astronomers call a low-mass X-ray binary. It consists of a black hole with a mass between 6 and 7 times that of our Sun, along with a companion star that's less massive than our Sunday. The two objects orbit each other every 7.75 hours, an incredibly short orbital period that places them very close together. The story of V616 Monocerotis' discovery takes us back to 1975, when astronomical satellites detected an intense X-ray source that brightened dramatically over the course of a few weeks. This X-ray outburst was one of the brightest ever observed from a stellar source, temporarily making it one of the brightest X-ray sources in the entire sky. What caused this dramatic outburst? The black hole in V616 Monocerotis periodically strips material from its companion star. This material doesn't fall directly into the black hole, but instead forms an accretion disk, a swirling disk of gas and dust that spirals inward toward the event horizon. Friction within this disk heats the material to temperatures of millions of degrees, causing it to emit copious X-rays. Most of the time, V616 Monocerotis remains relatively quiet, but every few decades, instabilities in the accretion disk cause a sudden increase in the rate at which material falls toward the black hole. During these outburst phases, which can last several months, the system brightens dramatically in X-rays and even becomes visible in optical light, allowing astronomers to study it in detail. The last major outburst of V616 Monocerotis occurred in 1975. Since then, the system has been in a quiescent state with only minimal X-ray emission. But astronomers continue to monitor it carefully, knowing that another outburst could occur at any time, providing another opportunity to study the physics of accretion around black holes. What makes V616 Monocerotis particularly valuable for scientific study is its relative proximity and brightness during outbursts. When the system is active, astronomers can study the properties of the accretion disk in exquisite detail. They can observe how material spirals inward, how the disk's temperature changes with distance from the black hole, and how jets of material are sometimes ejected at near light speeds perpendicular to the disk. These jets are one of the most mysterious aspects of black hole physics. Despite being objects from which nothing can escape, black holes can paradoxically power some of the most energetic phenomena in the universe. The exact mechanism by which black holes launch these jets remains a subject of active research, but it's thought to involve the interaction between the spinning black hole, the accretion disk's magnetic field, and the intense gravitational forces at play. The companion star in V616 Monocerotis is a K-type star, somewhat cooler and less massive than our Sunday. It's locked in a gravitational embrace with the black hole from which it cannot escape. Over millions of years, the black hole will gradually consume material from this star, slowly but steadily growing in mass. The star, meanwhile, will eventually be reduced to a planetary mass object or perhaps completely consumed. When you look at V616 Monocerotis, or rather, when you look at the region of sky where it resides, since it's too faint to see with the naked eye, you're looking at a system that embodies one of the fundamental processes in astrophysics, the transfer of matter from one object to another under the influence of gravity. This process, called accretion, is responsible for some of the most luminous phenomena in the universe. From stellar mass black holes like V616 Monocerotis to the supermassive black holes at the centers of galaxies that can outshine all the stars in those galaxies combined. At approximately 6,070 light-years from Earth, in the constellation Cygnus the Swan, lies one of the most famous black holes in astronomy, Cygnus X1. This object holds a special place in scientific history as the first black hole to be widely accepted as real, transforming black holes from theoretical curiosities into confirmed astronomical objects. Cygnus X1 was discovered in 1964 during an early X-ray survey of the sky conducted by a sounding rocket. The source appeared as an intense point of X-ray emission, one of the brightest X-ray sources in the entire sky. For several years, astronomers debated the nature of this mysterious object. The breakthrough came in 1972 when astronomers identified the optical counterpart of Cygnus X1, a blue supergiant star designated HDE 226868. This star has a mass approximately 20 to 40 times that of our Sun and a surface temperature of about 30,000 Kelvin, making it shine with an intense blue-white light. But more importantly, this star showed periodic variations in its spectral lines, indicating that it was orbiting an unseen companion every 5.6 days. By carefully measuring the blue supergiant's orbital motion, astronomers could calculate the mass of its invisible companion. The result was unambiguous. The unseen object had a mass of approximately 21 times that of our Sunday. This far exceeded the theoretical maximum mass for a neutron star, leaving a black hole as the only plausible explanation. The confirmation of Cygnus X1 as a black hole was so significant that it inspired a famous bet between physicists Stephen Hawking and Kip Thorne. In 1974, Hawking bet against the existence of black holes in general, and Cygnus X1 in particular, a bet he was happy to lose as evidence mounted. Hawking conceded the bet in 1990, giving Thorne a subscription to Penthouse magazine, the agreed-upon stakes. The Cygnus X1 system is remarkable for several reasons beyond its historical significance. The black hole is actively accreting material from its companion star, making it one of the brightest persistent X-ray sources in the sky. Unlike V616 Monocerotis, which undergoes occasional outbursts, Cygnus X1 maintains relatively steady X-ray emission, allowing for continuous study of the accretion process. The blue supergiant companion is so massive and so close to the black hole that it fills its Roche lobe, the region of space within which material is gravitationally bound to the star. Material at the inner edge of this region can transfer onto the black hole through a process called Roche lobe overflow. Additionally, the supergiant generates a powerful stellar wind streams of particles constantly flowing away from its surface. The black hole captures some of this wind material, adding it to its accretion disk. One of the most intriguing aspects of Cygnus X1 is its spin. Recent observations suggest that this black hole is rotating at very close to the maximum rate allowed by physics, more than 95% of the speed of light at its event horizon. This incredibly rapid rotation has profound implications for the geometry of spacetime around the black hole and affects how material accretes onto it. The high spin rate also provides clues about the black hole's formation history. When a massive star collapses, If the collapse is asymmetric, as it often is, the resulting black hole can inherit significant angular momentum. The spin of Cygnus X1 suggests that the progenitor star was rotating rapidly when it collapsed, or that the black hole has gained substantial angular momentum by accreting material from its companion. Cygnus X1 also occasionally exhibits what astronomers call state transitions. The system alternates between different accretion modes, characterized by different ratios of X-ray emissions at different energies and different radio emissions from jets. These state transitions provide valuable insights into the complex physics of accretion disks and the launching of relativistic jets. The blue supergiant companion star in Cygnus X1 is itself approaching the end of its life. In perhaps a few million years, this star will also exhaust its nuclear fuel and collapse. Given its high mass, it will almost certainly form a black hole of its own. This will create a binary black hole system, two black holes orbiting each other, which will eventually spiral inward and merge, releasing tremendous gravitational waves in the process. When you contemplate Cygnus X1, 6,000 light-years away, you're contemplating a system that has taught us more about black holes than perhaps any other object in the sky. It transformed black holes from mathematical abstractions into physical realities, helped launch the field of black hole astronomy, and continues to provide insights into the extreme physics that governs these remarkable objects. At approximately 7,800 light-years from Earth, also in the constellation Cygnus, lies V404 Cygni, another remarkable black hole binary system. This object is famous for its extraordinary outburst behavior, producing some of the most dramatic X-ray flares ever observed from a stellar mass black hole. V404 Cygni consists of a black hole with a mass approximately 9 times that of our Sun, along with a K-type companion star somewhat less massive than our Sunday. The two orbit each other every 6.5 days, locked in a gravitational embrace that has continued for millions of years. The system first came to widespread attention in 1989 when it underwent a spectacular X-ray outburst, briefly becoming one of the brightest X-ray sources in the entire sky. During this outburst, the brightness increased by a factor of more than 100,000 compared to its quiescent state. Astronomers around the world trained their telescopes on this extraordinary event, gathering data that would help unravel the mysteries of black hole accretion. After the 1989 outburst, V404 Cygni returned to quiescence and remained relatively quiet for 26 years. Then, in June 2015, the system erupted again in an even more spectacular outburst. What made this event particularly extraordinary was not just its brightness, but its variability. The X-ray emission varied wildly over timescales of minutes to hours, sometimes brightening or dimming by factors of hundreds or even thousands in mere minutes. This extreme variability provided unprecedented insights into the physics of accretion around black holes. Astronomers observed the accretion disk becoming unstable, with material falling toward the black hole in chaotic, turbulent flows. The system exhibited what physicists call flaring behavior, Sudden, dramatic increases in brightness followed by equally rapid decreases. During the 2015 outburst, astronomers observed V404 Cygni across the entire electromagnetic spectrum, from radio waves to X-rays to gamma rays. This multi-wavelength campaign revealed an incredibly complex picture. The system was launching powerful jets of material at near-light speeds, jets that changed direction and intensity over periods of hours. The accretion disk was precessing, wobbling like a spinning top, causing dramatic changes in the appearance of the system as different parts came into view. One of the most remarkable observations during the 2015 outburst was the detection of optical flashes. For brief periods, V404 Cygni became bright enough to be visible with a modest amateur telescope, an extraordinary feat for an object almost 8,000 light-years away. These optical flashes were produced by X-rays from the inner accretion disk being reprocessed by material farther out in the system. The black hole in V404 Cygni appears to have a relatively low spin compared to objects like Cygnus X1. This suggests a different formation history or evolution. The lower spin affects how the accretion disk forms and behaves, potentially explaining some of the system's unusual characteristics. Between outbursts, V404 Cygni exists in a quiescent state, emitting only weak X-rays and appearing as an unremarkable star when viewed in optical light. But astronomers continue to monitor it carefully, knowing that another outburst could occur at any time. These outbursts are thought to be triggered by instabilities in the accretion disk, specifically changes in the disk's temperature and ionization state that suddenly allow material to flow inward more rapidly. The unpredictability of these outbursts is part of what makes V404 Cygni so fascinating. Unlike some variable objects that have regular, predictable patterns, V404 Cygni's outbursts appear to occur at irregular intervals. The 26-year gap between the 1989 and 2015 outbursts was followed by several smaller outbursts in subsequent years, suggesting that the system's behavior is more complex than simple periodic eruptions. The study of V404 Cygni has revolutionized our understanding of how black holes accrete matter in extreme conditions. The data gathered during its outbursts have been used to test theoretical models of accretion, to understand the formation and evolution of relativistic jets, and to probe the geometry of spacetime close to the event horizon. As you contemplate this remarkable system, nearly 8,000 light-years distant, consider the light that reaches us from V404 Cygni. The photons we observe today began their journey toward Earth around the time humans were developing agriculture and settling in the earliest cities. The black hole has been consuming material from its companion star continuously throughout all of human history, occasionally erupting in spectacular outbursts that briefly make it one of the brightest objects in the X-ray sky. Before we delve into the mysteries these black holes conceal, let us visit one more fascinating system, XTE J1118 plus 480, located approximately 6,000 light-years away in the constellation Leo. This black hole holds special interest because it appears to be what astronomers call a halo black hole, a black hole that exists not in the main disk of our galaxy but in the galactic halo, the spherical region surrounding the disk. XTE J1118 plus 480 was discovered in March 2000 when it underwent a dramatic X-ray outburst that made it visible to X-ray telescopes around the world. The outburst lasted several months, during which astronomers gathered extensive data about the system. Since then, it has returned to quiescence, but the information gathered during that outburst continues to provide insights into black hole physics. The black hole itself has a mass between 6 and 7 times that of our Sun, similar to V616 Monocerotis. Its companion is a K-type star, somewhat cooler and less massive than our Sunday. The two orbit each other every 4.1 hours, one of the shortest orbital periods known for any black hole binary system. This extremely short period places the two objects very close together, close enough that tidal forces from the black hole significantly distort the shape of the companion star. What makes XTE J1118 plus 480 particularly intriguing is its location in the galactic halo. Most stellar mass black holes we know of reside in the galactic disk, where the majority of stars are found. Black holes in the halo suggest different formation scenarios or evolutionary paths. This system might have been ejected from the disk through gravitational interactions, or it might represent an ancient population of black holes that formed early in the galaxy's history. The velocity of XTE J1118 plus 480 through space provides clues about its origin. The system is moving at approximately 140 kilometers per second relative to the local standard of rest, significantly faster than typical disk stars. This high velocity supports the idea that the system was ejected from its birthplace, perhaps by the supernova that formed the black hole or through subsequent gravitational interactions with other stars. During its 2000 outburst, XTE J1118 plus 480 exhibited interesting spectral characteristics. Unlike many black hole binaries that show strong optical emission during outbursts, this system remained relatively faint in optical wavelengths even as it blazed in X-rays. This led astronomers to conclude that the accretion disk in this system has unusual properties, possibly related to the low metallicity of the companion star. Metallicity, the abundance of elements heavier than hydrogen and helium, affects how gas behaves in accretion disks. The companion star in XTE J1118 plus 480 appears to have a lower metallicity than the Sun, suggesting it formed from primordial gas that hadn't been enriched by many previous generations of stars. This provides another piece of evidence that the system is quite old, possibly formed when the Milky Way was young. The study of XTEJ 1118 plus 480 has contributed to our understanding of black hole jets. During its outburst, the system launched relativistic jets, streams of particles moving at significant fractions of the speed of light. Radio observations tracked these jets as they expanded outward from the black hole, allowing astronomers to measure their speed and study their properties in unprecedented detail. One of the most remarkable aspects of the jets from XTE J1118 plus 480 is their apparent superluminal motion. When observed from Earth, the jets appeared to be moving faster than the speed of light. This isn't a violation of Einstein's relativity, it's an illusion created when a jet moving at near light speed happens to be pointed almost directly toward us. The geometry causes the jet material to nearly keep pace with the light it emits, creating the illusion of faster-than-light motion when projected onto the plane of the sky. The black hole's mass and spin have been measured through detailed analysis of its X-ray spectrum during outbursts. These measurements suggest a moderately spinning black hole, rotating at perhaps 40–60% of the maximum possible rate. This intermediate spin provides constraints on the black hole's formation and accretion history. XTEJ 1118 plus 480 also serves as a laboratory for studying the physics of accretion at very low rates. In its quiescent state, the accretion rate is extremely low, perhaps a billionth of a solar mass per year. At such low rates, the standard models of accretion disk physics begin to break down, and different physical processes become important. Studying quiescent systems like this helps astronomers understand the full range of accretion phenomena. The companion star in this system faces an uncertain future. It's gradually losing mass to the black hole, and over hundreds of millions of years it will be substantially depleted. Eventually, it might be reduced to a brown dwarf or even a planetary mass object, a ghost of its former self orbiting an invisible black hole. The system will become even harder to detect, perhaps eventually joining the population of isolated black holes drifting unseen through the galaxy. As you contemplate XTEJ 1118 plus 480, imagine this system's journey through cosmic time. It was born perhaps billions of years ago, possibly in the dense stellar environment of the galactic disk. It was then ejected, perhaps violently, to wander through the galactic halo. For millions or billions of years, it has journeyed through that emptier region of space, occasionally accreting material from its companion, rarely erupting in outbursts like the one we observed in 2000. The system connects us to the early history of our galaxy, to a time when the Milky Way was young and stars were forming from nearly pristine gas. It demonstrates that black holes aren't confined to any particular region of the galaxy, but can be found throughout its vast volume, from the dense central regions to the sparse outer halo. Moving deeper into our catalogue of nearby black holes, we encounter GROJ 1650 Fiva-40, located approximately 11,000 light-years away in the constellation Scorpius. While farther than some of the other systems we've discussed, this black hole has provided some of the most dramatic observations of any stellar mass black hole, particularly regarding the jets it produces. GRO J 1655-40 was discovered in 1994 by the Compton Gamma Ray Observatory during an X-ray outburst. The system consists of a black hole with a mass of approximately 6.3 times that of our Sun, along with a companion star that's slightly more massive than our Sunday. The two orbit each other every 2.6 days, a relatively short period that indicates they're quite close together. What made GRO J 1655-40 immediately famous was the observation of spectacular jets during its 1994 outburst. Radio observations revealed two blobs of material racing away from the black hole at apparent speeds exceeding the speed of light, another example of superluminal motion. In this case, the jets were observed to be moving at speeds corresponding to about 92% of the speed of light, and their orientation relative to our line of sight created the illusion of even faster motion. These observations were groundbreaking because they provided some of the clearest evidence yet that stellar mass black holes could produce jets similar to those seen emerging from supermassive black holes at the centers of galaxies. The jets from GRO J 1655-40 demonstrated that the jet launching mechanism operates across an enormous range of black hole masses, from stellar mass objects like this one to supermassive black holes billions of times more massive. The black hole in GRO J 1655-40 has a high spin, rotating at approximately 70% of the maximum possible rate. This rapid rotation plays a crucial role in powering the jets. The leading theory for jet formation, called the Blandford-Znajek mechanism, relies on extracting rotational energy from the spinning black hole through electromagnetic processes. The rapid spin of this black hole makes it particularly efficient at launching powerful jets. During its various outbursts, the system has erupted several times since its discovery. GRO J 1655-40 has exhibited the full range of accretion states that black hole binaries can display. It has been observed in the hard state, where X-ray emission comes primarily from high-energy photons and steady jets are present. It has been seen in the soft state, where the accretion disk dominates the emission and jets are suppressed. And it has been caught during transitions between these states, providing crucial data about the physics governing these changes. One of the most interesting aspects of GRO J 1655-40 is what it tells us about the supernova that formed the black hole. Detailed studies of the system's motion through space reveal that it's moving with an unusually high velocity, about 112 kilometers per second relative to nearby stars. This high velocity, combined with other evidence, suggests that the supernova that created the black hole was asymmetric, giving the newly formed black hole a kick that sent it speeding through space. These supernova kicks are thought to be common when massive stars collapse. If the explosion isn't perfectly symmetric, and observations suggest they rarely are, the black hole can receive a momentum kick from the ejected material. In the case of GRO J 1655 a -40, this kick was strong enough to substantially alter the system's orbit through the galaxy while still keeping the binary system intact. The companion star in GRO J 1650 Fiv-40 is an F-type star, somewhat hotter and more massive than our Sunday. It's slowly being stripped of its outer layers by the black hole, gradually losing mass through both Roche-Lobe overflow and through the capture of its stellar wind. Over cosmic time, this star will evolve and eventually die, though its ultimate fate depends on its current mass and how much material it loses to the black hole. Observations of GRO J 1650 Fiv-40 during outbursts have revealed fascinating details about the inner accretion disk. X-ray spectroscopy can detect ion emission lines from material in the disk, and the shape and energy of these lines provide information about conditions very close to the event horizon. The lines are broadened and distorted by the extreme velocities of the orbiting material and by relativistic effects including gravitational redshift and light bending. These observations allow astronomers to map the structure of the inner accretion disk with remarkable detail. They can measure how fast material is orbiting at different distances from the black hole, how the temperature of the disk changes with radius, and how the disk's geometry is affected by the black hole's spin. Such detailed observations are possible for only a handful of black holes, making each one precious for testing our theoretical models. The system has also contributed to our understanding of the connection between accretion and jet launching. By observing GRO J 1650 Fiv-40 across multiple outbursts and across different wavelengths, astronomers have been able to track how the properties of the jets change in response to changes in the accretion flow. This has helped refine theoretical models of how magnetic fields in the accretion disk and around the black hole contribute to jet formation and collimation. Between outbursts, GRO J 1650 Fiv-40 enters a quiescent state where it emits very little radiation. But even in quiescence, the system continues its orbital dance, with the companion star steadily orbiting the black hole. Astronomers continue to monitor it, knowing that the next outburst could occur at any time and provide another opportunity to study these remarkable phenomena. When you contemplate GRO J 1655 -40, 11,000 light-years distant, you're contemplating a system that has taught us profound lessons about the most energetic phenomena in the universe. Those jets, racing outward at nearly the speed of light, carry energy extracted from the black hole's rotation itself, demonstrating nature's ability to tap into the most fundamental properties of spacetime. Now that we've explored these specific black holes, our nearest cosmic neighbors, and some slightly more distant but equally fascinating systems, let us turn our attention to the deeper question posed by our journey. What do these black holes hide? What mysteries do they conceal within their dark boundaries? The most fundamental mystery of black holes relates to their singularities, the infinitely dense points at their centers where all the collapsed mass is theoretically concentrated. Our best theories of physics, general relativity, and quantum mechanics give contradictory predictions about what happens at a singularity. General relativity suggests that density and curvature become infinite, while quantum mechanics insists that infinite quantities cannot exist in nature. This conflict suggests that our understanding is incomplete. Most physicists believe that a theory of quantum gravity, a framework that successfully merges general relativity and quantum mechanics, will be necessary to fully understand what exists at the heart of a black hole. Until we have such a theory, the true nature of the singularity remains one of physics' deepest mysteries. Several approaches to quantum gravity have been proposed. String theory suggests that what we perceive as point-like particles are actually tiny vibrating strings, and that at the center of a black hole, spacetime itself might be replaced by a complex structure of strings and higher dimensional objects called branes. Loop quantum gravity suggests that spacetime has a granular structure at the smallest scales, which might prevent the formation of true singularities. Other approaches, including causal set theory and asymptotic safety, offer their own perspectives on how to resolve the singularity problem. But without the ability to directly observe the interior of a black hole, prevented by the very nature of event horizons, we can't empirically test these theories. The singularity remains hidden, not just by the event horizon, but by the limits of our current theoretical framework. It's a mystery that represents both the boundary of our knowledge and the frontier of theoretical physics. The event horizon itself conceals mysteries beyond the physical state of the singularity. Once anything crosses this boundary, it is lost to us forever. Information about its quantum state, its composition, its history, all of this seems to disappear into the black hole. This led to what physicist Leonard Susskind called the black hole information paradox. According to quantum mechanics, information cannot be destroyed. The state of any system can, in principle, be reconstructed if you know the complete quantum state of all the particles involved. But if information falls into a black hole and can never escape, doesn't this violate this fundamental principle? Physicist Stephen Hawking initially argued that information was indeed destroyed in black holes, but this led to such profound problems with the foundations of quantum mechanics that physicists have been searching for alternative explanations ever since. Hawking's later work suggested that black holes aren't completely black after all. Through a quantum process now known as Hawking radiation, black holes should very slowly emit particles, eventually evaporating completely over timescales far longer than the current age of the universe. If this radiation somehow encodes the information about everything that fell into the black hole, then perhaps information isn't destroyed after all, but the details of how this encoding works remain mysterious. Recent theoretical work has explored various mechanisms by which information might be preserved. Some physicists propose that information is somehow stored at the event horizon itself in quantum correlations that are released in the Hawking radiation. Others suggest that black holes might form quantum entanglement with particles outside the horizon, allowing information to be preserved in subtle correlations. Still others propose more radical solutions, such as the possibility that information might somehow tunnel out of the black hole through quantum effects. The resolution of the information paradox may require us to fundamentally revise our understanding of space, time, and information itself. Some physicists have suggested that space and time might be emergent phenomena arising from more fundamental quantum information. In this view, black holes are teaching us that reality at its deepest level is about information and its flow, rather than about particles moving through space. Each of the black holes we've explored tonight might be surrounded by quantum fuzz, a region near the event horizon where quantum effects become important. In this zone, the smooth space-time of general relativity might be replaced by a foaming, bubbling quantum structure. The exact nature of this quantum fuzz and how it affects infalling matter remains a subject of intense theoretical research. The concept of quantum fuzz arises from attempts to reconcile quantum mechanics with general relativity near the event horizon. At scales approaching the Planck length, about 10, -35 meters, quantum fluctuations in spacetime itself should become significant. Near the event horizon of a black hole, these fluctuations might create a complex structure that could affect how the horizon behaves and how information is processed as matter crosses it. Some physicists have proposed that this quantum fuzz might replace the smooth event horizon of classical general relativity with something more complex, a firewall of high-energy particles, or a fuzzball of quantum strings, or some other exotic structure. Each proposal has different implications for what happens to matter and information as they encounter the black hole. These ideas remain speculative, testable only through indirect means. Future observations of black holes, particularly through gravitational wave astronomy and possibly through the detection of Hawking radiation from primordial black holes if they exist, might provide clues about the nature of the event horizon at quantum scales. Another profound mystery relates to the interiors of spinning black holes. When a black hole rotates, the structure of its interior becomes more complex than the simple picture of a singularity at the center. General relativity predicts the existence of what's called an inner horizon, beyond which the laws of physics as we know them might break down entirely. In the case of a rotating black hole, described by the Kerr metric, the singularity is not a point, but a ring, a one-dimensional circle in space. The geometry near this ring singularity is extraordinarily strange. Some solutions to Einstein's equations even suggest the possibility of shortcuts through space-time wormholes, though whether these could actually exist in nature remains purely speculative. The ring singularity in a Kerr black hole creates what's called the Cauchy horizon, an inner boundary where predictability breaks down. In principle, if you could somehow survive crossing the outer event horizon and falling toward the inner horizon, you would encounter a region where the usual notion of cause and effect might not apply. Time-like loops might exist, and the future might not be uniquely determined by the past. However, most physicists believe that these strange features of the Kerr solution might not actually occur in nature. Small perturbations, any slight irregularity in the inflowing matter or fields, tend to be amplified enormously as they approach the inner horizon, potentially creating what's called a mass inflation instability. This instability might prevent the formation of a stable inner horizon, replacing it with something else, perhaps another singularity, or a region where quantum effects dominate. The black holes we've explored tonight, Cygnus X1, GROJ 1655-40, and others, are all rotating at significant fractions of the maximum possible rate. This means their interiors should have this complex geometry with inner horizons and ring singularities, assuming the classical theory holds. But what actually exists inside these black holes remains hidden behind their event horizons, accessible only to theoretical speculation and mathematical analysis. The black holes nearest to us also hide clues about stellar evolution and the deaths of massive stars. Each black hole we observe represents the endpoint of a stellar life, but many details of how massive stars collapse remain uncertain. What determines whether a dying star forms a neutron star or a black hole? What happens in the final moments before the collapse? How much mass is lost in the supernova explosion versus how much ends up in the black hole? Recent discoveries of black holes with unexpected masses have deepened these mysteries. Some stellar mass black holes have been found with masses in a range that theoretical models suggested should be rare or impossible, the so-called mass gap between the heaviest neutron stars and the lightest black holes. The discovery of black holes in this mass range has forced astronomers to reconsider their models of how massive stars die and how their cores collapse. The process of core collapse itself remains incompletely understood. When a massive star's iron core can no longer support itself against gravity, it collapses in a fraction of a second, releasing an enormous amount of gravitational binding energy. Most of this energy is carried away by neutrinos, but a small fraction, perhaps 1%, is deposited in the outer layers of the star, driving the supernova explosion. But the details of how this energy transfer occurs, how the bounce of the collapsing core translates into an outward moving shockwave that explodes, the star remain a subject of intense theoretical and computational research. Different models make different predictions about how much mass ends up in the resulting black hole and how much is ejected into space, affecting our understanding of the population of black holes in the galaxy. Some massive stars might collapse directly to black holes without producing bright supernovae at all. These failed supernovae would create black holes while ejecting little material into space. If this process is common, there might be a significant population of massive black holes that formed quietly, without the fanfare of a supernova explosion. The quiescent black holes like Gaia BH1 and BH2 hide another mystery. How common are they? If most black holes exist in quiet states, not actively consuming matter and not producing X-rays, how many might be lurking in our galaxy that we haven't yet detected? Some estimates suggest there could be hundreds of millions of stellar mass black holes in the Milky Way, most of them floating alone through space, invisible except for their gravitational effects. If this is true, then black holes are far more common than we currently realize, and the ones we've detected represent only the tiniest fraction of the total population. The discovery methods we currently use are biased toward finding certain types of black holes. We find accreting black holes through their X-ray emission, and we find black holes with companions through the gravitational effects on those companions. But isolated black holes drifting through space with no companions and no material to accrete remain essentially invisible to us. Future missions might change this. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will be capable of detecting black holes through gravitational microlensing, the temporary brightening of a background star when a black hole passes in front of it. This technique is sensitive to isolated black holes and could potentially reveal the true population of black holes in our galaxy. Each isolated black hole represents a complete mystery. We know nothing about its history, its properties, or even that it exists. How many such objects exist in our cosmic neighborhood? How many have passed relatively close to Earth over the billions of years of our planet's history? These questions remain unanswered, hidden by the fundamental invisibility of isolated black holes. The actively accreting black holes like V404 Cygni, Cygnus X1, and GROJ 1655-40 hide mysteries about the physics of extreme accretion. Why do some systems undergo dramatic outbursts while others maintain steady emission? What triggers the state transitions observed in systems like Cygnus X1? How do magnetic fields in the accretion disk affect the flow of material? How exactly are relativistic jets launched from regions near the event horizon? The physics of accretion disks involves a complex interplay of gravity, magnetic fields, radiation pressure, and hydrodynamic effects. The material in the disk is typically highly ionized, a plasma of electrons and atomic nuclei, which means it interacts strongly with magnetic fields. These fields can transport angular momentum outward through the disk, allowing material to spiral inward toward the black hole. But the details of this process remain incompletely understood. How exactly does the disk's turbulence arise? What role do magnetic instabilities play? How does the disk's structure change as the accretion rate increases or decreases? These questions require sophisticated computer simulations and detailed observations to answer. The state transitions seen in systems like Cygnus X1 represent particularly puzzling phenomena. The system can switch between different accretion modes, the hard state with strong jets and the soft state with bright disk emission, sometimes in a matter of days or weeks. What triggers these transitions? Current models suggest they involve changes in the accretion rate and the structure of the inner disk, but the precise mechanisms remain debated. The launching of relativistic jets represents another deep mystery. We know that jets are somehow powered by the black hole's rotation and the magnetic fields in the accretion flow, but the details of how this works are still being worked out. How is material accelerated to speeds approaching the speed of light? How are the jets collimated into narrow beams? Why do jets sometimes appear and disappear on short timescales? Observations of systems like GROJ 1000, 650 Fiv-40, with their dramatic superluminal jets, provide crucial constraints on jet models. By measuring the speed, composition, and energy of the jets, astronomers can test theoretical predictions and refine their understanding of these phenomena. But many questions remain unanswered, hidden in the complex physics of strong gravity, magnetic fields, and relativistic plasma. Perhaps most intriguingly, these black holes hide evidence of their own histories. By studying the masses and spins of black holes, astronomers can infer properties of the stars that formed them and the processes that have affected them since formation. A rapidly spinning black hole like Cygnus X1 tells a story of rapid rotation. The progenitor star was probably spinning quickly, perhaps because of tidal interactions with a companion or because of how it formed. When the star collapsed, this rotation was amplified. Conservation of angular momentum means that, as the core shrinks, it spins faster, just as an ice skater spins faster when they pull their arms inward. The mass of a black hole provides clues about its formation. A very massive stellar mass black hole, say 15 or 20 times the mass of the Sun, suggests a very massive progenitor star, probably a hot blue giant that lived fast and died young. A less massive black hole might have formed from a more modest progenitor. The distribution of black hole masses in the galaxy tells us about the population of massive stars and how they evolve. But the history of a black hole doesn't end with its formation. If a black hole has a companion star, it can accrete material and grow over time. This accretion can also affect the black hole's spin. Material falling into the black hole from a companion can add angular momentum, spinning it up, or if the material approaches from the opposite direction, it can spin it down. Some black holes might have had multiple companions over their lifetime. If a black hole formed in a dense stellar cluster, it might have interacted gravitationally with other stars, exchanging companions through complex gravitational dances. Each interaction would leave its mark on the system's properties, but those details are now lost, hidden in the current state of the system. Every black hole also carries with it the history of its accretion. Material that has fallen into the black hole over millions or billions of years has added mass, potentially changed its spin, and left no other trace of its existence. In a sense, black holes are cosmic garbage disposals, erasing all direct evidence of what they've consumed while slowly growing in the process. Imagine the history of a black hole like V616 Monosorotis or V404 Cygni. These systems have been accreting from their companions for millions of years, undergoing periodic outbursts. How many such outbursts have occurred over their lifetimes? How much mass has been consumed? What was the system like when it first formed, and how has it evolved to its current state? These questions are difficult to answer definitively, as we can only observe the system as it is now, not as it was in the past. There's also the tantalizing mystery of what we might learn from black holes in the future. The detection of gravitational waves from merging black holes, first achieved in 2015, opened an entirely new window on these objects. When two black holes spiral together and merge, they produce ripples in spacetime itself that carry information about the masses, spins, and orbital characteristics of the merging objects. Some of the black holes we've discussed tonight might themselves be part of binary black hole systems that will one day merge. When V404 Cygni's companion star eventually dies, if it forms a black hole, we'll have a pair of black holes orbiting each other. Over millions or billions of years, these two black holes will gradually spiral inward due to the emission of gravitational waves, eventually merging in a cataclysmic event that will send gravitational waves rippling across the universe. Current gravitational wave detectors like LIGO and Virgo have already detected dozens of black hole mergers, revealing a population of black holes with masses and properties that sometimes differ from what we observe in nearby systems. Understanding the connection between the black holes we can study in detail nearby and the black holes we detect through gravitational waves is an active area of research. Future detectors will be even more sensitive. The Einstein telescope, planned for construction in Europe, and Cosmic Explorer, proposed for the United States, will be able to detect black hole mergers at much greater distances and with much greater precision. Space-based detectors like LISA, Laser Interferometer Space Antenna, will be sensitive to gravitational waves from different mass ranges, potentially detecting mergers of intermediate mass black holes or even the inspiral of stellar mass black holes into supermassive black holes at galactic centers. These future observations will reveal the full population of black holes in the universe, from stellar mass objects formed from dying stars to intermediate mass black holes whose origins remain mysterious, to the supermassive black holes at galactic centers. Each detection will add to our understanding of how black holes form, evolve, and interact. The mysteries hidden within black holes extend to the very nature of space, time, and reality itself. Near a black hole, time slows down relative to distant observers, a consequence of Einstein's general relativity. For an astronaut falling toward a black hole, their own clock would seem to tick normally, but to someone watching from far away, the astronaut would appear to slow down, never quite reaching the event horizon, frozen at the boundary for eternity. This strange behavior raises profound questions about the nature of time and observation. Which perspective is correct? From the outside observer's viewpoint, nothing ever crosses the event horizon. From the infalling observer's viewpoint, the crossing is inevitable and happens in finite time. Black holes force us to confront the fact that reality itself may be observer-dependent in fundamental ways. These mysteries are not merely academic puzzles. They go to the heart of our understanding of the physical world. Every black hole is a laboratory where nature conducts experiments in extreme physics, creating conditions we can never replicate on Earth. By studying these objects, we're not just learning about black holes, we're learning about the fundamental laws that govern all of reality. As we approach the end of our journey tonight, let's step back and consider how these nearest black holes fit into the broader cosmic picture. They are not isolated anomalies, but part of a vast population of stellar mass black holes distributed throughout our galaxy and beyond. Current estimates suggest that our Milky Way galaxy contains somewhere between 100 million and 1 billion stellar mass black holes. This sounds like an enormous number, and in absolute terms it is. But consider that our galaxy contains roughly 200 to 400 billion stars. Black holes, despite their abundance, represent only a tiny fraction of the galaxy's mass and stellar population. Most of these black holes exist in isolation, drifting through space without companions, invisible and undetectable, except through their gravitational effects on nearby stars or gas. The black holes we've discussed tonight, those with companion stars that allow us to detect and study them, represent only the tip of the iceberg, a small sample of the total population that happens to be detectable with current technology. The distribution of these black holes throughout the galaxy follows certain patterns. They tend to be concentrated in regions where massive stars form and die, such as the galactic disk, where spiral arms contain dense molecular clouds. They're also found in globular clusters, ancient spherical collections of stars orbiting in the galactic halo, where close encounters between stars can lead to the formation of exotic black hole binaries. Over cosmic time, black holes play an important role in galactic evolution. Though individually small, their collective gravitational influence affects the motion of stars and gas. Black holes in dense stellar regions can interact dynamically with their surroundings, occasionally ejecting stars or even other black holes from clusters through gravitational interactions. The black holes nearest to us also connect to phenomena on much larger scales. The supermassive black holes at the centers of galaxies, millions or billions of times more massive than stellar mass black holes, grew through a combination of gas accretion and mergers with other black holes. Every stellar mass black hole that falls into a galactic center adds to the growth of the central supermassive black hole, linking processes on stellar scales to galaxy-wide evolution. When we observe the nearest black holes, we're also looking at objects that will exist far into the future. While stars shine for millions or billions of years before dying, black holes, once formed, will persist essentially forever. Even accounting for the slow process of Hawking radiation, stellar mass black holes will take longer than 60 years to evaporate, many orders of magnitude longer than the current age of the universe, which is merely 13.8 billion years. This longevity means that black holes formed early in the galaxy's history still exist today, silent witnesses to cosmic history. Some of the black holes in our galactic neighborhood might have formed when the Milky Way itself was young, when the universe was less than 1 billion years old. They've drifted through space for over 12 billion years, surviving countless interactions and orbital changes, eventually ending up in their current locations where we can observe them. The study of nearby black holes also connects to our search for gravitational waves. The LIGO and Virgo detectors have revealed a population of merging black holes, with masses and properties that sometimes differ from what we observe in nearby systems. Understanding the connection between the black holes we can study in detail nearby and the black holes we detect through gravitational waves is an active area of research. Future missions and telescopes will undoubtedly reveal more nearby black holes. The Gaia spacecraft continues to gather data, and follow-up observations of suspicious stellar motions will likely uncover dozens or even hundreds of additional black holes. Future X-ray telescopes with greater sensitivity will detect fainter accretion signatures, revealing black holes that are consuming material at very low rates. New gravitational wave detectors will probe a different range of black hole masses and distances. Each new discovery adds to our understanding not just of black holes themselves, but of stellar evolution, supernova physics, galactic structure, and fundamental physics. The nearest black holes serve as Rosetta Stones, helping us decode the physics of these mysterious objects and extrapolate that understanding to black holes throughout the universe. They also serve a more poetic purpose. They remind us of our place in the cosmos. We live on a small planet, orbiting an ordinary star in a typical spiral galaxy. Around us, scattered through space, are these invisible monuments to stellar death, objects so dense and strange that they challenge the limits of human comprehension. Yet we can study them, measure them, understand them to some degree. This ability to comprehend the universe, to make sense of objects millions of times more massive than Earth and thousands of light years distant, represents one of humanity's greatest achievements. As our journey draws to a close, take a moment to reflect on what we've discovered. We've traveled from the nearest black hole, Gaia BH1, at 1,560 light-years, to more distant neighbors like V404 Cygni at nearly 8,000 light-years. We've met quiescent black holes silently orbiting companion stars and active systems that erupt in spectacular outbursts. We've contemplated the mysteries these objects conceal and their place in the cosmic tapestry. There's something paradoxically comforting about black holes. They represent the universe at its most extreme, yet they follow predictable mathematical laws. They seem alien and frightening, yet they're natural products of stellar evolution, as inevitable as the changing of seasons or the phases of the moon. They exist in unfathomable darkness, yet by their gravitational effects on light and matter, they reveal themselves to our instruments and our understanding. The black holes nearest to Earth pose no threat to us. The closest one is still more than 14 quadrillion kilometers away. The gravitational influence of these objects extends only a relatively short distance into space before becoming negligible compared to other forces. They're not cosmic vacuum cleaners ready to devour everything around them. They're simply very dense objects with strong gravitational fields, obeying the same physical laws that govern everything else in the universe. Yet they do exert a pull not on our physical bodies, but on our imagination and curiosity. Black holes have captured the human imagination precisely because they're so far outside our everyday experience. They force us to think about the nature of space, time, gravity, and matter in ways that challenge our intuitions. They represent the ultimate unknown, the ultimate mystery. In studying these objects, we're following a tradition as old as humanity itself, looking up at the night sky and wondering. Our ancient ancestors looked at the same stars we see today and wondered about their nature. They created myths and stories to explain the cosmos. We've replaced myths with mathematics, but the sense of wonder remains. The black holes we've explored tonight remind us that the universe is both knowable and mysterious. We can calculate their masses, measure their spins, predict their evolution, yet fundamental questions about their nature remain unanswered. This combination of knowledge and mystery is what drives scientific inquiry forward. As you drift toward sleep, let your mind wander among the stars we've visited tonight. Picture Gaia BH1, our nearest neighbor, orbited by its sun-like companion star. Imagine V404 Cygni erupting in one of its spectacular outbursts, briefly blazing across the X-ray sky. Contemplate the rapid spin of Cygnus X1, distorting spacetime around it in ways that Einstein predicted, but that still challenge our imagination. Remember that while these objects are far away by human standards, they're our neighbors by cosmic standards. They're part of our galactic community, fellow residents of the Milky Way. The photons reaching our telescopes from these systems connect us across vast distances, carrying information about objects and phenomena we can never visit but can study and understand. The darkness of black holes is not an absence, but a presence of mass, energy, and mystery. It's a darkness that teaches us about light, about gravity, about the fundamental structure of reality. It's a darkness that, paradoxically, illuminates our understanding of the universe. Sleep now, and perhaps dream of cosmic journeys, of stars and darkness, of the delicate dance between matter and space-time. Dream of black holes silently drifting through the galaxy, of accretion disks glowing with the heat of friction, of event horizons marking boundaries beyond which no light can return. Dream of the universe in all its mystery and grandeur. The black holes will still be there tomorrow, patient and eternal, waiting for the next generation of astronomers and physicists to probe their secrets a little deeper, to understand them a little better. They've been there for millions of years, and will remain for millions more, silent guardians of nature's deepest secrets. Rest well, cosmic explorer. The universe is vast, mysterious, and wonderful, and you've taken one small step toward understanding a tiny corner of it. The nearest black holes to Earth, though hidden in darkness, have revealed to us some of the most profound truths about the cosmos and our place within it. May your dreams be filled with stars and wonder.